organized together because one, they basically affect the intestine, and two, because they have to do with inflammation. It's clear that celiac sprue is a different disease than irritable bowel syndrome, but it turns out that ulcerative colitis and Crohn's disease are also two very distinct diseases. They are grouped together because they end up giving the same symptoms, but for very different reasons. All right, so let's look at the small intestine. Basically, the intestine consists of villi, and if we focus in on those villi, you see an epithelial cell. So this is a section of this villi right here, and this is the epithelial cells. And there are little villi called microvilli. You're seeing them here, and they have this brush-like appearance, so they're called the brush border. Now, if we look at the villi, they're primarily consist of epithelial cells called enterocytes, and those are the absorptive cells. So that's most of the cells. Now, down in here in what is called the crypt are stem cells. And so what happens is that the stem cells migrate up through the tip of the villus, and as they migrate, they're differentiated, okay? And this takes about 24 hours. So when they get to the top, they then slough off, and they're replaced by another enterocyte. And this rapid turnover is one of the reasons that chemotherapy affects the intestine so intensely, because a lot of chemotherapy for cancer is directed at rapidly turning over cells, and that is the intestine. Now, in addition, you have goblet cells that secrete mucus. So they're surrounding the villi and the microvilli here with thick coating of mucus, which tends to hopefully trap pathogenic bacteria and then wash them away. Okay, let's go down here. So down in the crypt, I said there are stem cells, but there are also endocrine cells. Okay? And so they secrete GLP-1, which is an insulin secretagogue, cholecystokinin, which stimulates pancreatic and bile secretion, and also dampens appetite. So cholecystokinin is thought to be one of the culprits in why women get morning sickness, because during pregnancy it slows down digestion for the purpose of allowing the mother to take full advantage of the diet. So the slower you digest, the more efficient it is, and an outcome of that can be nausea. Now, somatostatin is another endocrine agent, and its job is to turn off the effects of GLP and cholecystokinin. Okay, where are the Paneth cells? Somehow I lost Paneth cells on this. Huh. Okay, so also down here are Paneth cells, and those cells are the cells that react to microbial infestation and secrete into the mucus surrounding the villi the alpha defensin, so antimicrobial peptide. Okay. So, and they're also secreting TNF alpha and other inflammatory agents. Okay. All right. So off we go. Okay. So we're going to start with celiac sprue. Again, it infects the small intestine. It's very common, about 1% of the population, mostly females, 2-to-1 ratio of females to males. It has a heritable component. So about 35% of monozygotic twins will each have celiac sprue. Okay? But this heritable component is necessary for a large part of the population, but it's not sufficient. Okay, so if 95% of the people with celiac sprue have this variant, this DQ2, DQ8 variant, that doesn't mean that everybody who has the variant will get celiac sprue. Okay, so about 6% of the people with the variant get the disease. Okay. Again, it's like the other diseases we're going to see today. It is a reaction of the immune system, but in this particular case, the triggering agent is known, okay? And that's gluten and other peptides like gluten. So gluten comes from wheat, but other carbohydrate grains give similar peptides that cause celiac sprue, okay? Inflammatory, and it's chronic and incurable. And if you don't treat it, it leads to morbidity and mortality. Okay, so let's look at one of the offending agents is gluten, which comes from wheat. And I'm going to talk in a minute about what gluten is. But you have other compounds coming from rye and barley, which do the same thing. So it's not just wheat. The jury is out on oats. So that's controversial whether oat flour will cause the same disease. But where are we? Corn, rice, and buckwheat are not toxic. So if you have a reaction to gluten, rye, barley, oats, is one thing. You can go and eat corn, rice, and barley. Now the reason for this is that if you take flour, let's say you're making bread dough or pizza, and you take that flour that you've kneaded, and you go take the flour and you put it in water, and you extract the carbohydrate from it, be about 2/3 of the mass will go away. What you will be left with is a rubbery, sticky substance called gluten, okay? And gluten, and there it is, gluten, okay? Gluten consists of two compounds, gliadin and glutenin. And they can be separated with ethanol. So if you extract that rubbery stuff with ethanol, you'll end up pulling out the gliadin. And gliadin is highly toxic. So we just refer to gluten, right, which contains gliadin and glutenin as being toxic, but it's really a lot of gliadin. Now, the interesting thing here, it's the primary structure, okay? Not secondary or tertiary structure. It's the amino acid sequence. And this is a gliadin peptide. And when you look at this, you see there are different sections of this peptide which cause different pathological outcomes. So for example, the red is cytotoxic, the gold is immunomodulatory, blue is gut permeating, right? And green is pro-inflammatory. So this peptide has built into it, this polypeptide, shorter peptides which have these deleterious effects, particularly if you're allergic to them. So this gliadin is particularly resistant to proteases. It has a very high proline content, which makes it survive the stomach and the gut and get into the intestine. And then when it is hydrolyzed, it produces these short peptides that do these various things that are basically not good. Okay, so what happens? So we look at gluten. So again, you're going to be generating a bunch of peptides. Some are immunogenic, others are toxic for various reasons. Normally, your gut is impermeable to these peptides, but if you're allergic, some of them get through a transcellular route. That means they go through the enterocyte and end up in the lamina propria, where the immune cells are sitting. They cause oxidative stress as they're doing this. Now that oxidative stress is going to modulate gene expression, which can lead to what? Cell differentiation. apoptosis, and an altered tight junction. Okay, so the tight junctions are the cells adhering to each other to prevent anything entering the system by other than the transcellular route. So anything coming in must go through the cells, therefore have to be transported, and they just can't go in willy-nilly. But because of this, these actions, what happens is these immunomodulatory peptides get through and they stimulate an abnormal immune response. Now that, along with the toxic peptides, again, alters that tight junction. Now once that happens, then there's a free-for-all, where the peptides now can get in through the transcellular route, more so than they did in the first place, but also get through the paracellular route. In other words, the tight junctions have been altered, have been compromised, and so now your gut becomes leaky to these peptides. And that's going to kick up the immune response and the oxidative damage. So it's a vicious cycle. Now, in addition, if we look at the DQ mutations, what's going on here is that there's an enzyme called tissue transglutaminase, and it cross-links these peptides from gliadin to the DQ-DQ8 HLA, and that makes them even more immunomodulatory. So that also will stimulate the immune response. We get a hyperaction to the immune response set off by these peptides. And again, remember, it's not just wheat. Okay, so, all right, so let's look at this. So this is just, a little bit more detail. So again, remember, oxidative stress causes a lot of the damage. Okay. The gliadin peptides enter, causing pro-inflammatory and oxidant conditions. They turn on NF-kappa B, and as you know, NF-kappa B will produce inflammatory cytokines. Okay, so these are associated with celiac disease. NF-kappa B also turns on COX-2 and lipoxygenase. So remember, COX-2 is the cyclooxygenase that is inducible and associated with pro-inflammatory outcome. Okay, so when you take Tylenol or Aleve, what you're trying to target is COX-2, which has been induced to give you that headache or fever. And again, what the COX-2 and lipoxygenase do is produce pro-inflammatory eicosanoids. So these come back, and of course are going to set off a cyclic condition which basically ramps up this abnormal immune response. Now, tissue transglutaminase, remember that's the enzyme that was cross-linking the DQ with the gliadin peptide, also downregulates PPAR gamma. And the outcome of that is that PPAR gamma will normally inhibit NF-kappa B. So we've seen this with the vitamin D receptor. So there's a feedback that prevents NF-kappa B from producing pathological inflammatory response. And one of them, in this case, it's PPAR, okay, another type 2 nuclear receptor, and that is blocked by tissue transglutaminase. Now let's take a look at what happens to your intestine. So here's a normal villus, okay, and this villus has been invaded by leukocytes or lymphocytes. By lymphocytes, and ultimately what happens is you end up getting crypt hyperplasia. So down here is the crypt. You see here, there's a very clear crypt, it's very delineated, and And here now, the crypt is responding, and look how it's thickened. So in this crypt, don't forget, we have the stem cells and the pannate cells. Okay? Now, as the disease progresses, you get increased degradation of the villus. So what you're looking at here is progression of celiac sprue. So ultimately, you go from a delineated intestine to over here, where you can see you have really thickened crypt and virtually no villus left. Okay? So the outcome of this is very predictable. It's going to be malnutrition and malabsorption. Okay? Plus there's going to be chronic diarrhea and other events. Because, again, why are you going to get chronic diarrhea? You cannot absorb nutrients, you cannot absorb fat, water, etc. And so you end up with diarrhea and malnutrition. Okay? So destruction of the villus. Now, that popped up, nutrient malabsorption, I just said that. So it's one of the outcomes is you're going to have failure to thrive because of nutrient malabsorption. Okay, so from this you can predict the effects, right? So in early childhood, diarrhea, abdominal distension, and again, failure to thrive. And that'll happen whenever you cannot absorb nutrients. After you develop the symptoms later in life, as you can imagine, fatigue from lack of energy, diarrhea, weight loss. So here it's failure to thrive when you're a child, but as you get older, you're going to have abnormal weight loss, anemia, and also neurological symptoms. Okay? So lifelong disease, no cure. You've got to watch your diet with increased morbidity and mortality if it isn't controlled. Okay, so now there are ways of controlling this, and one of them is through diet. So if you look here, some dietary components like vitamin C, polyphenols are antioxidants. So remember, pro-oxidation or oxidation is one of the primary causes of this. So the gliadin peptides are causing oxidant formation. So you can use antioxidants. The other thing that works is cutting down on inflammation. Okay? So omega-3. So remember, we talked about omega-3 as being important because for two reasons, in that they tended to generate, not to generate the more inflammatory eicosanoids. Okay? And so they generated eicosanoids that were less pro-inflammatory. And then also pointed out that the omega-3 polyunsaturated fatty acid also generate these three compounds here, protectins, resolvins, and myricins. And these are inflammatory resolving compounds. So these are one of the ways that the body turns off inflammation, right? The other was the rapid turnover of inflammatory eicosanoids. And then there's this way where you actually produce compounds that antagonize the pro-inflammatory agents. So again, that is why it's important to have omega-3 in the diet and certain anti-inflammatories. All right, so with that, we're going to charge into irritable bowel disease. All I have to do is get my computer to. Okay, good. All right, there we go. All right, so here we are, irritable bowel disease. Again, two diseases related in so much as they have very similar symptoms, but they're different diseases. The first difference is what part of the colon they impact. So in ulcerative colitis, talking about the transcending colon and the descending colon. Okay. Restricted pretty much to those areas. Crohn's disease pretty much affects the right colon or the ascending colon, but in point of fact, it can impact any part of the digestive system. So it can impact the stomach and the entire digestive system. Up here are shown the places where it is mostly affected, okay? So the ileum, the colon, etc. So it mostly affects around here, but any part of the digestive system. So that's one big difference between these two diseases, okay? Both inflammatory diseases and very, very prevalent, okay? Now, morphological differences. So if we look at a normal colon, we see these haustra. Okay? These are these little pouches here. So if you look at a colon, it's segmented. And those are the haustra that produce this segmentation. You can see the villi, very normal villi. And here's a nice scope view of an intestine or a colon. Okay? Now, we're going to compare these to the next set are in Crohn's disease. And look at the difference here. You can see this thickening right here, these thickened cell walls, the fissure, okay? And something referred to as cobblestone. So you go down here, you see the fissure and the thickened cell wall, and also notice the degeneration of the villi. Okay? So malabsorption. Here is a sample, a human sample, and you can see the cobblestone. Very, very different from the normal colon. Okay, now we move on and look at ulcerative colitis. You do not see a thickening, but you see ulceration and something called pseudopolyps. So let's just go down here and look at these pseudopolyps. So if you were to look at this, if you were a gastroenterologist and you were to do a scope, you would immediately see the difference between a normal intestine and Crohn's disease versus ulcerative colitis, even though the symptoms would be the same. And now if we look here, again, you don't see the thickening, but you see crypt distortion. Okay, so these are the crypts, not looking good at all. And once again, where are the villi? Okay, so you have a non-functional intestine. Okay, so what are the causes? There are basically three general causes, and that relates to environment, genetics, and microbiota. Okay, so the three of them come together to cause this disease. So environment, not only diet, but toxicants. Okay. So what are the toxicants we're faced with besides, say, pesticides or herbicides? Smoking, okay? NSAIDs. Now, why would NSAIDs exacerbate or be part of the cause of IBD? Yeah. Pardon me? Yeah, pretty much. It's antagonizing COX-1/2, but the result of that is what? We talked about why NSAIDs cause heart disease, right? Why isn't it a good idea for taking long-term NSAIDs, particularly high doses? What happens if you inhibit COX-1 and COX-2? Okay. Pardon me?
No.
Pardon me?
No.
No, actually, you get more inflammation. Why? Yeah, exactly. So what happens is you're still releasing those phospholipids like arachidonic acid, but now instead of going down the cyclic pathway, it goes down the linear pathway, right? So you're shifting the flux of metabolism from cyclic to linear, where before they were being shared. So you're augmenting the production of these pro-inflammatory or these inflammatory cytokines, such as leukotrienes, highly inflammatory. So that's why NSAIDs causes the problem. Why would smoking cause a problem? You're laughing like everybody knows smoking is toxic. But what is it about smoking that can think about environmental toxins? Smoking have any toxicants in it? What else? What is smoking? And don't forget, we talked about oxidation. So does smoking cause oxidation? Right? It does, right? There's a lot of free radicals in smoke. When you heat something up, you cause free radical formation, and that is pro-oxidant. So smoking is raising your oxidant level. Why would low vitamin D cause or contribute to irritable bowel disease? Yeah, so remember we talked about vitamin D as being an immune resolving compound, right? It shuts off NF-kappa B. Okay, so that all relates to why we think diet and environment are related to IBD. Let's see, genetics. Okay, so the problem here is that the genetics here is very, very complex. So with celiac sprue, it was primarily one mutation. Okay, in this disease, there are greater than 100 genes that differ. So it depends on the patient. And what do these genes do? Well, they do what you think they would do. And that is relate to immunity, cell-cell contact, autophagy, cytokine signal, the whole program here, pathogen recognition and processing, okay, TLR. So this is a pathogen recognizing receptor, and so is NOD. NOD is another pathogen-associated molecular pattern receptor. It's a mouthful, but it simply says that these two receptors recognize molecular patterns, that is peptides, from pathogens, and they react by causing inflammation. Okay, so very complex genetic program and dependent on the milieu of gut bacteria. Okay, so again, what is common to all these diseases? The breakdown of epithelial integrity and an immune over-response causing inflammation and tissue destruction. And you can predict from this what the symptoms are going to be, right? Abdominal pain, diarrhea, often bloody diarrhea, rectal bleeding, and malnutrition. Of course, you have a problem of increased incidence of colorectal cancer from this. Okay, so if they're going to stop appropriate differentiation, that can be an outcome. Now, to get further into the causes of this, 100 years ago, communicable diseases were the cause of most human death. Okay? Now, non-communicable diseases cause most human death. Okay? So that's a pretty enormous shift. Now, part of the reason for that shift is the introduction of antibiotics. So they've been very helpful. However, their overuse might have contributed to this shift in the types of diseases that are now killing us. So let's take a look at this. Again, diet, microbiome, and toxins. So we already really covered the toxicants: cigarette smoke, pesticides, etc. Drugs, that can induce cytochrome P450. Remember him? That's the 70 genes that are programmed or that occur in the human, which are responsible for biosynthesizing cholesterol and steroid hormones, activating vitamin D, regulating vitamin A, and a host of other beneficial problems. If you induce those genes, the cytochrome P450 genes, you then induce excessive catabolism of micronutrients and other compounds we need, okay? So drugs will induce a class of compounds that will go overboard and ridding ourselves of vitamin D, vitamin A, and other steroid hormones, etc. But let's get to the microbiome. So as said here, we've had a shift in society from natural childbirth to cesareans. And what the problem with that is as a baby undergoes natural childbirth, they are infected or populated with their mother's bacteria. Okay, so most of us have the bacteria in our gut came from our mother, and it is immutable for the most part. So the whole idea is that even if you're involved in an intimate relationship with another human being, you're going to maintain the bacteria you got from your mother. Okay? And if anybody here have a baby who changed a diaper? No one? Okay. So one thing you'll notice when that first infant, when you change the diaper in the first 3 weeks to 6 weeks, it is not an unpleasant experience. But after that, it is a total act of love. I mean, you ever smell the baby's diaper. And the reason for that is during that time period, the microbiome is establishing itself in the gut. Okay, so it isn't instant. The baby picks up the microbiome through natural childbirth and also through breastfeeding, because breastfeeding is not a sterile activity. And then when that microbiome begins to populate the gut and do its job, then you wish somebody else were changing those diapers. Okay? But now we don't do that a lot. With the decrease in natural childbirth and breastfeeding, and the overuse of antibiotics. Okay, so antibiotics prevented us from dying of communicable diseases. There is certainly a downside to their overuse. Okay, and that is basically an attack on our microbiome. And the idea of parents worrying that the little kid is going to get germs, and so they practically sterilize the little guy all the time, rather than allow him to have some exposure to bacteria, which primes the immune system. So we talked about a J curve before, right? Where during aging, there is a theory that a little bit of stress is good because it primes us to deal with it. And you could say the same thing here, that exposure or limited exposure to microbiota is good because it primes and develops the immune system. Okay? So then it goes into saying, where are we getting our microbiome today? And it may be from sources that aren't very good. Okay, so what happens? The barrier is compromised. So you go down here, and it starts with a diffusion of luminal bacteria into mucosa. So this is similar to celiac sprue. The microbiome starts compromising the intestine, perhaps because we picked up the wrong microbiome. It causes inflammation. The inflammation compromises the intestinal barrier, and then you get an enhanced diffusion of microbiota pass through the intestinal lumen, which sets off this vicious cycle of inflammation and tissue injury. All right, Western diet. Okay, so this is just sort of a subtext of what we talked about diet, and it's thought that a milky diet, high fat, high carb, ends up feeding or being deficient in short chain fatty acids. And these are the sort of fatty acids that commensal bacteria thrive on. And the result of that is that you have an increase in pathological microbiota. And again, all of the rest of this is just going through what I have just said, and that is if you switch from commensals to pathological, you're going to have an inflammatory response that ruins the intestinal barrier. And so the other side of that is if we cut down on some of the worst parts of our diet, we can basically kick up our commensal bacteria at the expense of the pathological bacteria. So it's just a variation on the dietary. Oh, here we go. I get pop-ups that tell me I'm not allowed to move them. Sorry about this. Bear Bears wants me to join them. I don't want to.
No, I know this is part of this. It's only good. I feel like I should.
And we're back. Okay, so let's talk about NOD, because one of the common mutations, as I said, there are 100 different genes in GWAS studies, but NOD is one of them. And NOD, well, first of all, we'll go back to this again. So the pannate cells are secreting defenses into the mucosa, okay? And so together with the mucosa sweeping away the bacteria, and the defensins, you're protecting yourself against pathological bacteria in your intestine, okay? And again, MAMP here is microbial associated molecular pattern, is the same thing as PAMP, right? The pathogen associated molecular pattern, just a little bit more specific. And so when the pannate cells sense this MAMP, through toll-like receptors, they then, in association with MyD88, produce an antimicrobial pattern, okay? This is the way things are supposed to work normally. Now, when we look at Crohn's disease, you first see that we have a NOD2 receptor here. So again, this is similar to TLR in that it senses these microbial patterns and basically sets off NF-kappa B to produce defensins, okay? And this MDP is just one of these microbial associated molecular patterns. Okay, so this is the normal way of doing things. And then if you have a NOD mutation, you're not going to get an inflammatory response through this particular pathway, and you're not going to produce defensins, okay? So now you have, because of this mutation, enhanced invasion of pathological bacteria, right? So this is straightforward. Turns out that it's a little bit more complicated than this, because remember, whenever we turn on an inflammatory response, you have to turn it off, or else. And that's what this slide here is showing. So a little bit more detail, showing that the NOD receptor, right, is sensing this microbial pattern, turning on NF-kappa B, which produces defensins. So far, so good. Now, In addition, you have toll-like receptors which also sense these MAMPs, okay? And work through MyD88 to produce NF-kappa B, right? So you have these cells by two different pathways, right? The NOD receptor and the TLR, the toll-like receptors, reacting to these bacterial patterns, kicking up the immune system. Now, if you look here, what you see is that the cells also truncate or attenuate NF-kappa B action, okay? So it's not just turning on, it's turning on NF-kappa B, but it's also ultimately turning it off. Okay? So we have a nice little thing going on here. We're producing defensins, and then we're turning off the NF-kappa B so we do not get chronic inflammation. So what happens if you have a NOD mutation? You get a decrease in defensins. That's obvious. So that means you're not going to be able to fight those bacteria that are invading when they shouldn't be coming through the transcellular route. But you're also not going to be turning off the inflammation, right? So you have an enhanced bacterial load causing excessive inflammation, and the inflammation is not resolved. And this is all because of the NOD2 receptor mutation. So again, when you stimulate NF-kappa B, you need to turn it off or you're in trouble. And in this particular case, it's not direct, but NF-kappa B does lead to producing proteins that turns off its own expression. Okay? Any questions about that before I charge on here? Okay. All right, so treatments. Again, knowing what I should say the cause. We know the cause of these diseases in broad strokes, not, so you're really treating symptoms, okay? Glucocorticoids, anti-inflammatory. So why are glucocorticoids anti-inflammatory? How, we had a lecture on this of how glucocorticoids affect their anti-inflammatory action. Okay. Think about, yeah.
Pretty sure it was the inhibition of phospholipase.
Yes, that's true. So what he said was an inhibition of phospholipase A2, right? So remember, NSAIDs are inhibiting COX, and that only inhibits the cyclic pathway and allows the flux to go down the linear pathway, but glucocorticoids turn off phospholipase A2, so it stops inflammation by cutting off substrate to everyone. So that's why glucocorticoids work here. Free radical scavengers, antibiotics, even though maybe antibiotics was a problem in the first place, this is getting rid of those pathological bacteria. Thiopurines, this is a cancer chemopreventive agent, which inhibits the turnover or the production of rapidly dividing cells. So it inhibits immune cell proliferation. PXR, which regulates innate immunity, we're going to see that. Antibodies, so their actual, some treatment is you take antibodies to TNF-alpha, right? A highly inflammatory cytokine, and you dose the people with these antibodies, okay? And the only thing, and then of course we have other antibiotics. Ultimately, in some cases, nothing works, and they have to cut out the colon, and that can resolve the disease. Okay, so nuclear hormones. I mentioned PXR. We talked about PPAR and VDR. We talked about PXR. So PXR is also a type 2 nuclear receptor, just like PPAR and VDR. And the rest of these, well, not true. Glucocorticoids type 1, estrogen receptors type 1. Okay, so what happens is PXR will suppress NF-kappa B, and that suppresses the production of inflammatory cytokines, okay? So that's why PXR is effective. All right, I think that's about where I'm going to stop now. Again, we have a few minutes left, so this is time for questions. Anybody have any questions about this or anything else?